Well, today we're going to talk about the movement of particles and the motion of molecules and so on and so forth. And we're going to relate it to what's called the kinetic molecular theory. The kinetic molecular theory is an explanation of the behavior of molecules. So now when we come up with these theories, it's going to be explaining a certain portion of a particular behavior. Now, I want to go over real quick some misconceptions with the word theory because it's used incorrectly all the time. Most specifically with the climate change theory. You guys get the impression like a theory, it's kind of like, oh, that's just our best guess, right? I think the word's been used incorrectly for a very long time. The word theory does not mean that, well, we're working to trying to figure out exactly what's going on. That is not what the word theory means. The word theory is a collection of data and facts and things that actually happen in a way to explain the behavior of scientific phenomena. So what do you guys think? Do theories become laws? I think that's what people think, is that they think that if a theory is actually figured out to be true, that it turns into a law. And we're going to separate that in our brain. A theory does not mean it's not true. It is the current explanation in as great of detail as we know right now. Can anybody think of a law of nature? Law of conservation of energy. That means that matter is not created nor destroyed. Anybody else? How about law of gravity? Law of gravity says if I stood here and I dropped something, it would fall to the ground, right? It always happens. Theories and laws are completely different things. Theories do not become laws. Laws are a description of what will happen. So a law is just stating what's going to happen. A theory is an explanation why it happens. So laws are what, theories are why. So theories are actually going to be what you would use to describe why a law was happening. Does anybody know why the law of gravity is true? Does anybody know anything about gravity? Pretty beneficial to us. It's a pull that one body has on another body based on its mass. So you guys have probably heard that your weight on Earth is going to be different than your weight on the moon. Does anybody know, do you weigh more or less on the moon? You weigh less. If you were unsure, you could kind of think of, have I ever seen those videos of the people walking on the moon where they're kind of bounding, you know? That's because you weigh less on the moon. And the reason you weigh less on the moon is because the moon is a smaller piece of rock, I guess. So it's the size of it. But even you guys sitting here have gravitational attraction to each other. So the why is the theory. Why is it that if I hold something in my hand and I let go of it, it will fall to the earth? You would have a theory to describe why the law of nature would happen. So theories doesn't mean they're not true. It just means that it's an explanation why, and it can never be proven. In science, we never really say we prove things. We can build on it and improve it, the theory, but it doesn't mean it's not true. Can anybody think of another theory now that you learn kinetic molecular theory? How about the easiest one? Big Bang Theory? Are there people who don't believe in the Big Bang Theory? There are. Does anybody know what the opposing theory is to Big Bang Theory? You might. Let's think about it. Big Bang Theory states that the universe was created by one big cosmic expansion of nuclear energy spreading out into other kinds of energy. Good morning. Here, I'm going to give you this. And I'm going to have you sit at a lab table. Just pick one with the yellow square in it. We're going to do a seating chart, Izzy, but I'm going to wait until everybody gets here. So if there's a particular seat that works better for you, just email me. So there's a lot of people who don't believe in the Big Bang Theory. They think that God created the universe, right, in 7 days. Does that all sound familiar? So that's called the theory of creationism. That doesn't mean that the Big Bang Theory is incorrect. It just means that there's alternative theories out there, just like the climate change theory. A lot of people don't believe that that's true. But if you can find a scientist who does not agree with the climate change theory, I would be very surprised. Okay, anyway, let's go over some things that we already know about the phases of matter. The normal phases of matter, without the goofy ones like plasma, or some other ones that there's like semi-critical fluid. They're coming up with other states of matter. But for our purposes here, we only worry about solids, liquids, and gases. So solids have definite volume. Liquids have a definite volume, but gases do not. They take the shape of the container. They fill the container, which is bonus because you walk into my classroom and you never have to say, gee, I hope Miss Boston has enough oxygen in her room today. So you guys know that when you walk into this room, that we're all going to have enough oxygen to breathe. And that is thanks to our good old friend, gravity. Solids have a definite shape. Liquids have a definite volume, but they will fill whatever container you put them into a level of a specific volume. And gases fill the container. So here's the big differences between solids, liquids, and gases. Solids have definite shape and definite volume. Liquids have definite volume, but not definite shape. And gases have indefinite volume and indefinite shape. So solids have the particles really close together, touching. Liquids have a little bit of space in them. And gases have a large amount of space between the particles. So let's pay attention to this next one. All molecules are in motion at any given time. A molecule's in motion. So even the molecules in your desk, they're moving. They're vibrating and spinning in place. Does anybody know what it's called when all molecular motion stops? Do you know? It is. It's absolute zero. We haven't reached absolute zero yet. Does anybody think we'll get to absolute zero? We just haven't done it yet? Maybe on another planet, but that would violate one of the laws of nature, which we cannot. That's the laws of thermodynamics. So there's scientists who spend their entire career working on getting to absolute zero, knowing that they can't achieve that goal. Can you imagine working your whole career on something that you know can't happen? So solids have molecules that are moving slow, liquids are medium, and gases are fast. So if you have the same substance, a solid will have the lowest kinetic energy, liquids will be in the middle, and gases have high kinetic energy. So solids temperature increase means that if you heat up a solid, it expands very little. We know it does expand. If you're ever driving down the road, you ever see the road where it looks like it's a little bit crumpled or a little bit like a truck went over when it was too hot? And you'll see in sidewalks, they have cracks in them. The reason that we put the cracks in there is because otherwise you will get cracks in the sidewalk that when they expand, when it gets hot outside. Liquids, that's the same thing. They expand just a very little bit, but gases expand greatly with increased heat. Liquids and solids are not compressible, gases are. So, let's move on to the kinetic molecular theory. Kinetic molecular theory states that all matter is composed of tiny indivisible particles called molecules or atoms. Now, you might say to yourself, well, you taught us in the beginning that we can pull molecules apart and even atoms into protons, neutrons, and electrons. That's true. It's just not part of the kinetic molecular theory. Second assumption is that all molecules are in constant motion. So if you kind of see the movement of the molecules here, solids kind of just vibrate and spin in place. Liquids can flow past each other, or the molecules can slide past each other. And gases are all over the place. The next one is that collisions between molecules are elastic. That means that there's no transfer of energy as they collide or any heat released during the collision. Now, logic tells you, if you know anything about physics, that that's not possible. For every action, there's an equal and opposite reaction. But molecules are so small that we can ignore that addition to it to make our problems more straightforward. The next one is that molecules are not attracted nor repelled from each other. You'll also learn later on in chemistry that this is also not possible. But it's one of those things that we can ignore to make a problem a little bit simpler, because the attractions don't change the way gases behave that much. And then the last one is that temperature is related to the kinetic energy. So we need to make sure that we're understanding the difference between temperature and heat. This whole thing is going to be related to the difference between temperature and heat. So remember, temperature measures the average speed or kinetic energy of the molecules. So a thermometer is actually kind of like a speedometer for those molecules. Heat is something different. It is definitely related to it, but if you want to know what heat is, you grab the leg of your desk and you're going to feel what heat is. So which way does heat travel? Travels from hot to cold. Now, if you go out on the street and you ask 10 people on the street which way does heat travel, they're probably going to say it travels up, right? Have you ever stood at the bottom of a mountain? What's on the top of the mountain? Snow. Clouds and snow. You think it's warmer up there with all the heat traveling up there? It's not. So heat always goes from hot to cold. Heat does not travel up. So if you grab the leg of your desk, you're going to feel the heat traveling down, aren't you? Leg of your desk is below you. The heat's traveling down because your hand is at 37 degrees Celsius and your desk is, does anybody remember what room temperature is about? 21. Yeah, about 72 degrees Fahrenheit. But let's see if we can try to get comfortable with degrees Celsius so we can at least, when we go to other countries, you go to other countries, don't ask anybody to change anything to Fahrenheit for you. Because they're going to be like, what? What's this Fahrenheit you speak of? So the reason that the heat, your desk leg feels cold is that your hand is hotter. So you're feeling the heat leave your hand. That's what it feels like. There's no such thing as cold. It's only the absence of heat. So why do people think that heat rises? Well, if you go to your house and you have different floors in your house, you'll notice the basement's always feels colder, right? And it feels hotter upstairs. That's because hot air rises. And you try to tell that to somebody, they're going to be like the same thing. Heat and hot air are the same thing. No, heat is energy, hot air is matter. Two completely different things. So remember, heat does not rise, it travels from hot to cold. Temperature does not measure the amount of heat. Temperature measures the speed of the molecules. So if they've never gotten to absolute zero, let's talk for a quick second how they figured out what absolute zero is. Well, they extrapolated the graph backwards of pressure versus temperature. I'm going to do a lecture for you real quick a different day, and I'll probably record it for you, where we discuss the difference between the Celsius temperature scale and the Fahrenheit temperature scale. So heat is the flow of energy due to temperature differences, and we measure that in joules or calories. So density of material changes, so specific heat is different for different temperatures and different substances. So the larger the value, the longer it takes for the substance to absorb heat, the longer it will keep the heat. That's called an insulator. An example of an insulator is water. Small values heat up quickly. It takes less time for them to heat up. They're good conductors, like metals. So when something heats up or gets hotter, the molecules are moving faster. When something cools down, the molecules are moving slower. And heat always travels from hot to cold. So temperature is a measure of the speed of the molecules. That's what you're supposed to get out of this lecture today. The difference between heat and energy and the speed of the molecules, as opposed to energy transfer due to hot and cold. So now we're going to move on to our blank heating and cooling curve. Let's remember, potential energy is stored energy or energy of position. It's going to be stored in the phase of the substance. What that means is that the position or phase of the substance is how close are the molecules to each other. Solids are very close. Liquids are medium. Gases have a high distance between each other. Kinetic energy is related to the temperature, so it's when the temperature is changing. So let's go to our graph and let's take some notes on the heating and cooling curve. So you notice on the x-axis, that's the independent axis. You're either going to see heat added or removed or time. And if you look on the y-axis, that's the independent axis, you'll have temperature there. Notice the two temperatures that we are interested in are 0 and 100. That is the freezing point and the boiling point for water. So let's look at the different phase changes. So when you have a slanted part of the graph, that's the temperature changing. And you notice we have our solid, liquid, and gas. Our solids are at low temperatures. Our liquids are at the medium temperatures. And at high temperatures, we have gas. The flat parts or the plateaus are where the phase is changing or the potential energy is changing, meaning all of the heat that we're adding is going towards rearranging the molecules. So between the solid and the liquid, to go from a solid to a liquid, you melt. To go from a liquid to a solid, you freeze. Hopefully all of these terms sound familiar. We're going to actually get a little bit greater detail about these phrases. Going from a liquid to a gas is called vaporizing or boiling. And going from a gas to a liquid is called condensation. So to condense something is to change it from a gas to a liquid. So the whole way when we're adding heat from left to right, if we're adding heat to a system, is that endothermic or exothermic? Putting heat into a system, it is endothermic. So from left to right, it's endothermic. That happens from adding heat. So from right to left, where you're removing heat, heat is leaving the system. That is exothermic. So let's think about that, people. When you freeze water, it is an exothermic process. So when you take liquid water and turn it to ice, it's actually going to release heat. So if anybody knows anything about, has anybody who lives in Florida, you know that it does freeze in Florida, right? So they have all those citrus plants that they need to worry about. So all sorts of oranges and lemons and stuff like that down there. If it freezes, it ruins the fruit. So very low-tech way to protect the fruit from being damaged by freezing conditions is to spray it with water. And then as the water freezes, it actually releases energy to the fruit and protects it. And ice is actually an insulator, so then it kind of keeps it from getting ruined and freezing itself. Okay, let's add these terms. When you're vaporizing, the amount of heat you need to add to a liquid to change it into a gas, that amount of heat is called heat of vaporization. Now look at the one that's confusing. Heat of fusion is the amount of energy you need to add to a solid to get it to be a liquid. That's the only one that can be confusing. So a lot of times I'll put the other three down and use process of elimination. So heat of solidification is a little easier one. Heat of condensation is easy. Heat of vaporization is easy. The one that can be confusing is heat of fusion. Do that one last. Now make sure you understand this. Heat of fusion and heat of solidification are the same quantity. It's just one has to be added and one has to be taken away. So the exothermic process is when heat is taken away from the system, and that would have a negative value. So heat of solidification and heat of fusion are the same value, but heat of solidification would have a negative sign. Heat of fusion would have a positive sign. Same thing with vaporization and condensation. They are the same quantity. It's just that heat of vaporization would be the energy we needed to add to get a liquid to go to a gas, and heat of condensation would be the energy we need to remove. So here's the important part. Make sure you label these. The flat parts or the plateaus are where our potential energy is changing. The slanted part is where our temperature is changing or the kinetic energy is changing. Notice there is no spot where the kinetic energy and the potential energy are changing at the same time. It's either one or the other. And here is a very concrete picture of the difference between heat and temperature, because the sections where we're changing potential energy is not changing the temperature. So even though we're adding heat, the temperature is not changing. That's proof to us that heat and temperature are not the same thing. So in sections A, C, and E, kinetic energy is increasing with added heat. In sections B and D, the potential energy is increasing with added heat. So only the slanted parts are where the temperature changes. In the flat part, the potential energy is changing. So link that up in your brain, that phase changes are with PE. That changes the position. All of those P's all match up with each other. Potential energy, phase change, position of the molecules, plateaus on the graph, all with P's. So if you link those up.